Well, hi everyone. Thanks for letting me give a talk. I did my PhD in Nijmegen in the Netherlands, and right now I'm doing a postdoc in the Oxford Computer Science department on a research project to use diagrammatic methods and graphical methods to do quantum compilation, which is what this talk is about as well. Okay, so let's get started. Yeah, so the idea is that we want to do quantum computing using certain types of pictures. Now, why I want to do that? Well, I think all of you here are familiar with quantum circuits, and these are these things that go from left to right. We have gates on them, which are usually labeled by some name, which like no specific gate, and these are quite useful. Like they're used a lot, right? But of course, there's like multiple circuits represent the same underlying computation. For instance, we have these cancellation rules and combination rules. Also, some gates commute with each other. So even if you cancel all the things, there's not a unique way to represent a gate to represent a circuit. Unfortunately, there's like more of these circuit inequalities, and there's even more, and there's even more. Okay, so why is this so terrible? Well, it's because the choice of gates is always a bit arbitrary. You always have to choose a set of gates, and there's always some set of rules that's in between those gates. You have to remember those rules, which is all hard. Also, the notation is not quantum native, because quantum circuits really came from classical circuits and Boolean circuits, and there's no a priori reason to believe that this should be the right language to talk about quantum computing, right? Like, it's nice, it works so well, but there's no reason it should work perfectly. And thirdly, like the wire is very rigid. Like we have a set amount of wires coming in, it's equal to the amount of wires coming out. They go from left to right, you can't bend wires, you can't combine wires. So it's a very rigid way to think about these things. Okay. So what I'm going to talk about in this talk is the ZX calculus, which is a related graphical language, which essentially allows us to get rid of these problems. Okay, so on the surface level, the ZX calculus, so ZX diagrams, are just an alternative notation to quantum circuits. So for every of these gates, we have this representation as a ZX diagram. So for instance, the S and T gates, well, they're both rotations about the Z axis of the log sphere. So you represent it in the same color, this green color, and S is a pi/2 radian rotation. T is a pi/4 radian rotation. X gate, well, that's a rotation over the x-axis. There's different axes represented with a different color, namely red. And then the C0 gate becomes this combination of a green and red dot, and it will become clear why soon. And we have a special notation for the Hadamard gates. And then translating a quantum circuit to a ZX diagram is just, you take each of these gates, you replace them with the thing, and then you just connect them in the same way. Okay. So what the ZX diagrams actually are, they are built out of spiders. So whereas quantum circuits are built out of circuits, these things are built out of spiders. And these are a particular type of linear map. It's a family of linear maps, which can have any number of inputs and any number of outputs. It's this particular sort of projection thing. It's kind of like a generalized Kronecker delta, if you know what that means, with like a phase attached to it. And the same thing, the X spider is the same thing, but with a different basis. Instead of the computational basis, we have the Hadamard basis here. So for instance, if you have a single input, single output Z spider with an alpha phase, well, this is just this thing, which if you write as a matrix, well, we get the sum of matrices, and this is just the standard Z rotation gate, which is why we had the Z rotation gates, the S gate and T gates in the green color on top here. And similarly with the red gates, yeah, if you think about this, you can recognize this as an actual X rotation gate over the phase alpha. Okay. And we can combine these spiders every way we like. So if we have the vertical composition, it's a tensor product of these linear maps. Horizontal composition is the composition of linear maps. So the same way as in quantum circuits. And we have these symmetries. So it doesn't matter which way we orient these things. It results into the same linear map, which is why we're allowed to write these sort of horizontal wires. In fact, there's this sort of meta rule for these diagrams that says that only connectivity matters. So we can deform these diagrams any way we want, and as long as we connect the same thing to the same things, and we preserve the order of the inputs and the outputs, it represents the same linear map. Okay, so we can sort of treat these things as undirected graphs. Okay, so to summarize this, we have two types of generators. We have the Z spiders and X spiders. We can compose them both horizontally and vertically, and we can connect wires any way we want. And like Z spiders and X spiders can have as many wires as we want. So it turns out this is a powerful representation because we can represent any linear map between qubits as a ZX diagram. So not just unitary maps, but any linear maps. So also states or post-selections or projections or isometries we can represent it all using a ZX diagram. Okay, so this is just notation so far, which is fine, but not super useful yet. Okay, so what can we actually do with it? Well, it comes equipped with a set of graphical rewrite rules. For instance, in the top left, we see that if we have two Z spiders or spiders of the same color that are attached by one or more wires, we can simply fuse these spiders together and like the faces add. And the Hadamard gate, this yellow box, we can push this through a spider and it changes the color of the spider and the Hadamard pops out the other end. Or this one says if we have a faceless spider with a single output next to a spider of the opposite color, we can push it through the spider and it explodes into this disconnected set. Okay, so like all these rules have a very graphical interpretation, like a very intuitive, makes sense. You can just look at it and see, oh, I can apply this rewrite rule here. Let me give an example. For instance, we have this thing which is a circuit which prepares a G8Z state, and we can prove it creates a G8Z state by converting it to a ZX diagram and simplifying it. So we can first translate it into a ZX diagram. So we have just gate-wise we translate, and then this zero state, this corresponds to a single output faceless red spider. And now we see we have these spiders which are the same color and they're connected to each other, so we can actually fuse them together. Now this is a single input, single output spider with a zero phase, which is kind of like a phase rotation gate over an angle of 0, which is an identity. So we can remove it. And again, we have these things which can be fused together. So we fuse it like this. Then we can push the Hadamard through this red one and it changes the color into green and the Hadamard pops out the other end, but there is no other end, so the Hadamard just disappears. And finally we fuse again. And yeah, this is a single spider and the definition is indeed equal to that of a G8Z state. Okay. The second example, this is the standard quantum teleportation protocol. So Alice puts in a state here and they do this protocol. So they share this maximally entangled state. They do some measurements. They have some quantum operations that are controlled on this classical outcome. And then Bob will be left with whatever Alice put in. And we can actually prove this diagrammatically. So first we translate it into a ZX diagram. And here I represent the measurement outcome by this A pi. So A is a Boolean variable. It's either 0 or 1, depending on the measurement outcome. And now we have these Z and X gates. And again, these are controlled by the classical outcome because we have, well, if A is 0, we don't apply a gate. It's just a 0 gate. And if A is 1, we apply a pi rotation, which is indeed an X gate or a Z gate. And this maximally entangled state just becomes this actual connection between this actual cup here. Okay, so we can start simplifying it. Well, first we fuse the spider with the same color. Then we change the color of the spider, and again we fuse spiders with the same color. Then we use our freedom to form a diagram, so we can remove this this little dangling wire. And again we fuse spiders with the same color. Well, then we see that if B is 0, it's just an identity, and if B is 2, well, it's 2 pi, which is also 0, so we can also remove it. And finally, we fuse these spiders, and we can also remove it. So we see that indeed whatever Alice puts in pops out on Bob's end. So yeah, we can graphically see that actually we're transporting Alice's state to Bob. Okay, so now a more complicated example. Suppose I give you the following circuit, and I ask you which qubits are entangled at the end. Now, there's multiple ways you can do this. You can calculate the matrix, for instance, because it's just 4 qubits. But like even staring at the vector you get, it's not essentially clear which are entangled. Okay, so another way we can do this is we write this as a ZX diagram. And this is a bit of a bigger ZX diagram. So let me use some software to actually simplify it. So I'm going to open up this software library called PyZX, which is a library I wrote together with Alex Kissinger. It's an open source Python library, which allows you to do large-scale diagrammatic rewriting of ZX diagrams. So this is a Jupyter notebook, which is sort of a graphical interface for Python. I'm going to first import PyZX. Then this is just a LaTeX representation of the same diagram, which is sort of a way to import it into PyZX and make it into a diagram. And now let me open it into the editor. All right. Okay, so we have the same diagram here. Okay, so let me start simplifying this interactively. So we have here these 2 spiders, which we can copy through. So we just copy them to a spider of the opposite color. And now we have all these spiders which can be fused. So we fuse the spiders. We have, let's see, we can push this string through to change the color. And we can fuse some more things here. So we fuse the spiders. We have an identity here, so let's remove the identity. Another identity is some fusions. Let me fuse some more spiders. Let me remove some more identities. Let me fuse some more spiders. Okay. Now this is sort of an internal thing, so it's actually, this is just a representation of a Y with a Hadamard. It's kind of a useful internal thing. Let's remove the identity. Let's see. So we're going to fuse this thing. And what we then get is, if this fuses, well, we have two wires between these. And the property of the ZX diagram is that if you have two wires between spiders of opposite colors, the wire just drops off. So I fuse this, and then the thing disconnects. And see, we can fuse this thing here. And this is just identities. Let's remove it. And we fuse this thing. And we fuse this thing. And we can remove the identity. Now I'm going to decompose this Hadamard into phases, so they cancel against the other phases there. And finally, I remove an identity, and I fuse a spider, and I fuse a spider. And we see that we end up with the first, third, and fourth qubit entangled, and the second qubit unentangled, just by applying these diagrammatic rewrite rules. Now, of course, I did this manually for demonstration, but we have built-in automated methods to actually do this for you. But I just want to give a little demonstration of what you can do with these things. Okay. So that was what I want to show. So we have a ZX calculus, which is a better representation of quantum circuits, if I may say so. And we can use it to graphically prove many things. So thank you for listening. If you want to learn more, I wrote this review article on ZX calculus, which contains the stuff I talked about today, along with a whole lot more. So if you want to learn more, check out the article, and thanks for listening.
Thanks a lot, John. That was a really cool talk, and I especially loved the demo at the end. I think that was a really nice touch. I was going to ask myself where people can learn more about ZX calculus, because this must be a completely new way of interacting with quantum circuits and quantum computing. But you've already shared the resource, so I guess that's already done. Are there any questions for our speaker at this point?
I just want to add, if you're a bit new to quantum computing and you want to have like a bottom-up approach, there is this book written by Bob Cook and Alex Kissinger, and it starts with no knowledge of quantum or physics at all. You just need to know what a matrix is. And it also uses ZX calculus to talk about quantum computing. So this is also a good way to start if you want to have a bit of more in-depth kind of explanation.
Thanks a lot. Yeah.
And you can also go to zxcalculus.com, and we have a lot of resources here to learn more. So
that's incredible. Thanks for sharing. All right, I think we have our first question. The question is there a manual to learn more about how to reduce circuits using ZX calculus? I believe that your resources somewhat explain that, but if you'd like to take a go at it.
Yeah, so in my review article, this ZX calculus for working quantum computer scientist, I really go into how you need to think about these things to simplify things. If you want to have specific publications, so we have on this website a list of essentially all the publications using ZX, which is quite a long list now. In particular, if you want to learn more about sort of automated rewriting of ZX diagrams, I suggest you check out this paper, Graph Theoretic Simplification of Quantum Circuits with ZX calculus.
Right, thanks a lot. And we have one more question for you. So the question asks, what would you say are some drawbacks of using ZX calculus compared to the current qubit system?
So there's a couple of things. First off, ZX calculus really likes talking about Clifford gates and phase rotations. And if your problem is described in terms of Clifford gates and phase rotations, you should use ZX because it's just superior to quantum circuits. If, however, you're doing stuff with Toffoli gates and multilinear logic, it is less useful but we have a related language, it's called the ZH calculus. And this allows you to more easily talk about toffoli gates. So that's a way to think. For instance, the trick of Craig Gidney with like the simplification with its toffoli gates and stuff, you can all prove that graphically in ZH calculus. I also go into that in this review article. But it's still, that's sort of like still, that's not super well developed yet. A other problem is that if you have a quantum circuit and say you want to simplify the quantum circuit, well, if you go to ZX diagrams, you can get a diagram out that doesn't necessarily look like a quantum circuit anymore. So you can't really run it on a quantum computer until you transform it back into a quantum circuit. So you have a quantum circuit, simplify it, get some diagram, and at some point you need to get a circuit out again. And this is a very non-trivial problem. And we have some techniques to do that, but in general, it's a hard thing to do.
Right, thanks a lot. I hope that answered all the questions. And once again, thanks, John, for your really engaging talk. I think you have another question. Maybe, all right, you can unmute yourself and go ahead and ask that.
Hi, John. So I was going through your paper, right? And I was working through the different rewriting techniques. And I was wondering how much of the thinking when you're doing these rewritings includes like thinking about matrix, because a lot of the spiders and whatnot are non-square matrix. And it doesn't fit with the kind of thinking I've been used to working with like quantum circuits, because in ZX calculus, you allow like different inputs and outputs to spiders, and that's kind of confusing for me. So what do you recommend?
So is the question, do I think about the underlying matrix when I simplify the ZX diagram?
Yeah.
No, I really think about the graphical nature. Like I sort of see patterns that I've seen before. Like, oh, if you have this pattern, it simplifies to this thing. Like it's really using like the fact that we are visual creatures and we can visually inspect something much more easily than we can inspect an equation or like, so for me, like this, I can rewrite this thing much more, like observe properties of it much more easily than from a matrix. But like I've had years of experience using specs diagrams, of course.
Right.
Yeah, of course, there are like normal forms for ZX diagrams, so you can always reduce a circuit to a certain normal form. And this is essentially this representation of an inline matrix. So then like you don't really gain much, because then it's just a matrix within a diagrammatic form.